very much, everyone. Thank you for the introduction, Rich, and thank you, everyone, for attending and for the opportunity to talk. I'm going to start with a selfie, though. If you don't want to be in it, put your hand over your face. This will end up on LinkedIn, so you have been warned. Now get me back to my timer, and then we can get going. There we go. Perfect. So thanks very much for the introduction. I'm Stephen Bates. I've done a lot of work with NVMe Express, which is something Samsung is obviously a leader in. You guys are shipping more NVMe SSDs by a considerable margin than anyone else on the planet right now. And behind those SSD controllers is this wonderful NAND that you guys make that is, certainly best in class. And you're to be congratulated for the achievements that you've made. I'm going to talk a bit about how these very fast PCIe devices are changing some of the, what I call the biorhythms of computer architecture. Our ability to move, process, and store data continues to evolve, and while we always get better, we get better at different rates, and that always affects the decisions around computer architecture. And we're in a very interesting time right now. I'm going to talk a little about why we're in an interesting time, and hopefully you'll agree. And then I'm going to show you some of the things that we're doing that we think help address some of these challenges that are being introduced by things like NAND and NVMe and PCIe and so forth. It is going to be humorous, so you are allowed to laugh from occasion. First thing I'm going to talk about is the fact that we've come a long way, baby, and I'd like everybody to give themselves a pat on the back because we're all part of an industry that's achieved some pretty amazing things over the last 30 or 40 years. I'm going to give you a little sense of that, and then I'm going to talk about the biorhythms of computer architecture and how they change our view on what a computer architecture should be at a given point in time. We've gone from phases of consolidating computers, mainframes and so forth. We've gone to disaggregation and moving everything apart, and we're going back to centralization with data centers in the cloud, and now we're moving back out again because of the edge. So we continue to do that. I'm going to talk about how the CPU has become the CPU, has become the CPU. You'll notice that they are getting smaller each time. I'll talk a little about that and explain what I mean by that. I'm going to finish with some real-world examples of things that my company and other companies are doing that I think are kind of interesting and maybe kind of showing how we approach some of the challenges that we're facing. Just a little bit about me. Rich already did the introduction, so you can basically take a picture of this as you're interested. But I've done a lot of work on VLSI and signal processing and error correction and so forth. Done a few startups. Some of them were great. Some of them were not so great. Been acquired a couple of times, haven't we all, etc. I did grow up in Belfast, and my favorite football club is actually a very small club near where my dad grew up. So that's kind of why I have a very random favorite sports club. I did get the privilege of doing my PhD in Edinburgh, and that was a lot of fun. So we have come a long way, baby. It's actually unbelievable how much computing has achieved, even in the last 20, 30, 40 years. And I'd like to give you a sense of that by talking a little bit about how far we've come, baby, in compute, storage, and networking, which for me are the three branches of computer architecture. How fast can we manipulate a bit? How fast can we move a bit? How fast can we store a bit? And how cheaply can we do these, and for how much power? So just to give you an example, in 1996, Hitachi deployed the SR2201. It was a supercomputer, and at the time, this was the most powerful supercomputer in the world, 1991. In today's money, it cost about $1 billion to build, and it did about 614 gigaflops. Today, a company called Samsung, you might have heard of them, launched the Galaxy S9. They sell it for about $850. You can probably get it for free with a 2-year plan from Sprint. Seem to get everything for free with a 2-year plan from Sprint. And it does 730 gigaflops. This was the most powerful computer in the world in '91. Literally everybody has one of these in their pocket today. Unbelievable. This is more powerful than this. The amount of scaling that we've achieved is absolutely phenomenal. Oh, and this is only part of the supercomputer. It took up a whole, half the floor of a pretty big building. It was, ridiculous. Storage, I like this one. I apologize. I did mean to put a Samsung disk in, but I couldn't find a terabyte. I'm sure you guys have a terabyte product, but I couldn't find it. So I apologize. And I was doing some of these slides at 4 this morning, so whatever. This is one of my favorite pictures. I ask a lot of people who are not super familiar with computing what they think this is. You guys are obviously much more familiar with computing, but this is a very early hard drive from IBM. And I love the fact the logo is actually on it. And say what you like about IBM, but they've been around a long time, and I think they will be around for a long time yet. This was 5 megabytes. Interestingly, a byte was 7 bits. I don't even know why, but anyway, Rob Pegler basically corrected me once and said it was not 5 megabytes as in bytes of 8 bits. In those days, we had 7-bit bytes, and I'm like, Rob, what the hell? But anyway, and in today's money, it would have cost you about $1 million US. And you didn't actually buy it, you leased it, and so forth. And literally, it weighed a ton. It literally weighed a ton, and it stored 5 megabits. Again, I apologize, this is SanDisk, but you guys do something very similar. 2018, this is a terabyte disk. I think this was the first terabyte SD card, and it cost $500 US. I think I worked out at some point what the order of magnitude improvement was, and it's 9 orders of magnitude improvement in terms of dollars per bit. And obviously, the physical space required to store a certain amount of data has also shrunk by similar orders. Networking, in 1886, they used a special kind of Morse code. The signal integrity of these undersea cables that they put between the UK, actually Ireland, and Newfoundland, because that was the shortest path. Those cables were absolutely terrible from a signal-to-noise ratio, so they couldn't use Morse code. They had to use this incredibly long Hamming code type thing. And they managed to achieve roughly 1 character every 2 minutes. So if you wanted to send a text message to the US in 1886, you could only send 1 character, 1 byte, every 2 minutes, which works out at about 0.064 bits per second. We can do a little better than that today. Google, Microsoft, and a couple of other companies laid a bunch of undersea cables. I think it was in the Philippines last year, and connecting basically Asia to the US. And on one of those sections, they were doing 160 terabits per second. So again, phenomenal orders of magnitude. I think if any other industry had done this level of improvement in the course of the last 50 years, it would be, respected and admired. Meanwhile, we literally get paid nothing for the things that we do, even though those things are absolutely unbelievably amazing, which is, still boggles my mind sometimes, but anyway. So if we take those last 3 slides, you can see that we have come a long way, baby. We've managed to achieve a lot. But as we move through those last 30 or 40 years, the relative performance of my compute, my storage, and my networking has been changing. So sometimes computers have been getting faster in terms of clock speed, for example, faster than my storage has been getting denser. So everything's been getting better, but at different rates. And so I like to call that the biorhythms. And I don't know if you're familiar with biorhythms, but they're this kind of, I don't even know really what they are, but they're these 3 attributes of your physical mind that you're supposed to kind of calibrate, and people treat it a little like astrology and whatnot, but I like to use it for computer architecture, and you end up getting 3 sine waves that have different phases and different frequencies. And those 3 line up sometimes, and sometimes they don't line up, and depending on how they line up, different things happen, apparently, in terms of your mood and so forth. So anyway, that's what people tell me. But from a computer architecture point of view, it does actually have an impact, because if something is improving faster than something else, it's going to change the decisions that are made at a computer architecture basis. Should I move my data to process it, or should I not? It's probably a function of how much it costs you to move data versus how much it costs you to process data. And those relative numbers are always changing. So the right way to do this is actually to have it like this, because everything's getting better, right? So, but that was kind of hard to do. But they're all getting better at different rates. And right now, we're entering a very interesting time. Some interesting things have happened. And I was at the RISC-V Summit this week, and I had some slides prepped. And then David Patterson gave a keynote, and I went, you know what, my slides are shit. I'm going to take pictures of Dave Patterson's slides and just show you those, because he can do this much better than I am. So I don't know if you know David, but he's retired now. He's a distinguished fellow at Google now. but he was a professor at Berkeley working on, wrote the book on computer architectures with Hennessy. And I think these are, he pointed out some of the trends that I think we're all familiar with. Single-threaded performance, i.e. how fast can I run one thread on one core, regardless of computer architecture or ISA, has stalled. In fact, it's got worse. That's because of Dennard scaling. I can't clock things faster because they will literally blow up, right? If I try to clock 7 nanometer at a really high frequency, then because of the threshold voltages and the current and the switching, I generate heat. That heat melts I was going to swear there, melts the silicon on which the computer is built. Dennard scaling says you cannot clock faster. And that's true. And in fact, David, I don't know if I have that picture of that slide, but he showed that the single-threaded performance has got worse. How did we fix that? We went multi-threaded. Hooray, we've got millions of cores. Right? And then everyone's like, how do you program with millions of cores? We invented SMP, coherency buses. We did a whole pile of work in software and operating systems. And that kind of helped for a while. We're like, OK, I can't clock one thread faster, but now I have libraries to help me write multi-threaded applications. And so I can kind of scale that way. But then along came Moore's law, which basically says you can't keep scaling the number of cores because you have a physical dimension into which you have to put all your bits. And that's not doubling it. I can't get double the transistors in the same physical area anymore. So the CPU has basically started to fail us. The assumption that my computer is always going to get faster and faster and faster is no longer true, and I think everybody in this room knows this, and it has been true for quite a while, and it's just getting more and more market. Okay. So what the biorhythms of computer architecture actually say is that the relative cost of moving data from the storage plane, for example, to the CPU plane to perform some computation on those bits, and then write the results back, in this case to the storage plane, but it could be to the network, are much higher than they have been. That's the relative cost. The absolute cost has continued to get cheaper, right? We're always getting better, baby, right? But the relative costs of these 3 different attributes of computer architecture are changing relative to each other. Right now, it's starting to make more sense to do compute closer to where the data actually is. And that's going to get me into the next part of this talk, talking about the rise of the smart devices. It actually makes sense to process data on the network card as the data is going into or coming out of the network. It's actually making sense to process the data on the SSD rather than doing a DMA to system memory and processing processing that data using instructions in a Xeon core or an AMD or an ARM or even a RISC-V. But the problem is, as we had when we first invented multi-core, is that the software frameworks we have no idea how to comprehend this. How do we program a SmartNIC to do something useful, given that we're used to writing C code and running it on an x86 or an ARM64? So it's really starting to tell us that the hardware has become a limitation, but now we're starting to address that. We have to start thinking about software again. We have to start thinking about paradigms by which we can program SmartNICs, we can program smart SSDs, and we can still have the operating system somewhere that's coordinating all of this and stepping in when error events occur. I still want to have my SSH and my Emacs and my Vim, if you're into Vim. I still want to have all my nice Linux-provided tools, but I also want to have this paradigm where I can program an FPGA to do some of my work for me. I can program my SmartNIC to do some of my work for me. I can program my smart SSD. We're going to need vendor neutrality. I do not want to have to program something differently because I'm buying a Samsung thing, not buying an Intel thing. As a software developer, that to me is unacceptable. I don't like lock-in. Right? I like it when Linux runs on ARM and x86 and on RISC-V and on something else, and it's going to be the same for devices. I do not want to have to recompile my code because I'm changing my SSD vendor. So we need to have standards. We need to have standards to achieve vendor neutrality. That's the only way you get an ecosystem, and without an ecosystem, things tend to die off. We're going to have to also have that neutrality because then we can make changes to the operating systems like Linux, VMware, Windows Server, so that they know how to ask these devices what their capabilities are and then know how to consume those capabilities in some way that achieves some improvement in performance. One way, somebody said this, I'm not even sure whether it was me or Rob Pegler, we argue over who said this. We were drunk in a bar. It's all about the software. In computing and computer architecture, it is always all about the software until you reach the limits of the hardware. Then it's all about the hardware, at which point it's all about the software again. So we're actually going from a transition where we've hit a wall on software, we've made adjustments in hardware, and now we're actually having to make new modifications to software. And that's kind of where this journey around smart devices has reached at this point. And we're literally starting that activity. It's a very exciting time, and I think Samsung has a really strong opportunity to be a real leader in this space. So the rise of the smart NICs. So I have Arnold Schwarzenegger here as the Terminator. We have these I/O devices. And what's interesting, and I'm sure this is totally illegal, it's not. So, I'm sorry this is on public domain, but don't sue me, sue something. ARM inside. You know, Intel have not captured any market share in the smart devices area. They've very much struggled. They've tried with Atom. ARM have been incredibly successful. I think it's 20 billion cores will ship with ARM this year. 20 billion devices with some form of ARM core. Now, often those will be small embedded devices, but we know that the smart NICs of the world, the ones that are available from Annapurna, from Broadcom with the Stingray, from Mellanox with the Bluefield, they're all ARM enabled. Smart SSDs, I used to work on SSD controllers at Microsemi. We've migrated from Tensilica to ARM there. You know, Samsung, I'm very sure, have a whole suite of SSD controllers, many of which are ARM-based. So ARM are doing incredibly well in that space. And those ARM cores are very capable. They can run, some of them can run full stack Linux. Some of them have MMUs. Some of them are application class processors. Others are more embedded, but they still have a lot of potential for functionality. And often they sit beside some kind of accelerator unit. So in an SSD controller, for example, you have a very powerful error correction engine that's managing the bits that are wrong on the NAND. Right? The dirty little secret about an SSD is that the media you're actually using is, for want of a better word, shit. Right? I used to characterize NAND for Microsemi, so I've seen how bad it is. And what it amazes me is that because of this beautiful SSD controller, we can turn a media that has 3 or 4% error rate and convert it into something that does a 10 to the minus 15 or even 10 to the minus 18 error rate. Unbelievable. That's an accelerator. That accelerator that's in that SSD could, in theory, be exposed to the operating system and used as a LDPC emulation device, if you wanted to. That's not where I'm going today. I'm not saying you should do that. But if you have, for example, a compression engine in your SSD, and your operating system has need for compression, perhaps there's a way of letting the operating system borrow that compression engine when the SSD doesn't need it, potentially. Here's some examples of devices that power ARNI. We have, this is the, and I'll talk about most of these in a little bit more detail in a minute. So Pankaj is here. This slide's for you. Fusion IO was a company that did some very amazing things, quite a considerable amount of time before the rest of us knew even or appreciated exactly what they were doing. So taking the whole idea of taking very powerful PCIe connected devices and doing very interesting things with them was probably inspired by, in some considerable margin, certainly in my mind, by some of the work that was done at Fusion IO. So they were the first to really see the potential of PCIe connected non-volatile memory, providing some kind of accelerator, putting things in the host, truly foundational stuff that I think the rest of the industry has finally caught up to. So that was kind of a shout out to them. But now, now we need to go standardize some of this stuff. And I'll talk about this a little more in a minute, but we're starting to really push on NVMe and SNIA to get a lot of the vendors in a room and work out how are we going to standardize this. And the way that I like to look at it is, if I'm a processor running, or if I'm using a processor that's running Linux, what are the open interfaces that are available to me, right? So if you look at an Intel processor, what are the interfaces I can design to? QPI? No, you can't. Intel will sue you. You're in violation of your license agreement if you try to put something on the QPI interface. Only Altera get to do that these days. That's a problem because that's a coherent bus, but it's not an open coherent bus. DDR, yep, that's an open standard. I could go and put a device off the DDR interface. People have tried. Canadian company called Diablo tried to do SSDs in DIMM form factor. They went bankrupt. Ethernet doesn't typically come straight out of the processor. And certainly high-performance Ethernet doesn't. We have these new interfaces. I like to call them, I used to call them until this week, OpenGen CCIX, or C6, OpenGen C6. But now I have to add the WD new one, which is called Extend, so now it's OpenGen C6 Extend. They're all coherent, they're all open, they all look incredibly like each other, and I'm sure they'll all die. PCIe. IDC tell us this year about 13.5 million servers are going to ship. Guess how many of them will have Gen Z? 2. They're both going to research centers, one at Dell, one at HP. How many of them will have PCIe? 13.5 million of them, right? PCIe is going to be on every single server this year, next year, the year after, the year after, the year after. We may start to see things like C6. I guarantee there's not going to be a processor vendor anytime in the near future that's going to say, I'm going to do all C6 and no PCIe at all, because that would be literally insane. Right? So PCIe is a good interface. But as we look at these interfaces, we have to ask the question, if I put a device on that interface, what is the mechanism by which I can advertise what my capabilities are? How do I tell the operating system on the processor what I can do? Can I do compression? Can I run Docker containers? Can I do erasure coding? Can I do something else? And then once we have that advertisement capability, how do programs, typically the operating system, but maybe user space, running on the host, actually take advantage of that in some kind of vendor-neutral way? So we basically started that process. And I really encourage you, if you're interested, to get involved. This is a press release. Again, don't bother reading it. You can see it later if you're really interested. Basically, a whole bunch of companies got together and said, we need a technical working group to focus on computational storage, i.e., how do we standardize some of this? And the main bodies that are going to be involved are SNIA, from a kind of overview of all the standards. And to be honest, I think a lot of the focus will be on NVMe, because that's really where a lot of the action is. You might have heard of this company. These are the founding members of that technical working group. So Bill Martin, who's one of your standards people, asked me to just say that if you're interested in learning more or getting involved in some way, Bill is the person to contact, and his email is there. There's also this little startup up here. And there's an interesting thing about this slide. There's a couple of companies that were not SNIA members and joined only because of this twig, which is awesome for us as the twig, because they have to pay a membership fee based on revenue, and these were not startups. So this is a company SNIA has been trying to bring in for years, and they finally joined because of computational storage. ARM. I wonder why. Remember the Arnie Terminator slide? Right? ARM see this as a huge potential opportunity for them. Xilinx, never a SNIA member before, joined solely to get into this game, right? And the other one that's very big was also Inspur. So Inspur are one of those ODMs that are trying to go up the chain. They're trying to get more value add. They see this as an opportunity for them to deliver systems that are more intelligent, more power efficient, and potentially better than their competitors. And these are just the founding members. We are expecting other people to join SNIA in order to take advantage of this kind of fresh greenfield driver. So we talked about PCIe. We talked about how that is really one of the most open interfaces we can design to, that we know all the servers are going to have. And if we talk PCIe and we talk storage, we have to talk NVMe, right? And one of the phrases I'm starting to use now is we potentially have NVMe as one driver to rule them all. NVMe is, as you know, is a storage-centric. Well, it's not I have a slide coming up on this, actually. It was originated around SSDs. People are already using it to talk to NICs. So you can take a Bluefield and you can make it present to the host as an NVMe controller. There's a little company called Annapurna that got bought by a little company called Amazon. And the reason why was because they were doing this several years ago. They were taking networking devices and exposing them as NVMe endpoints. And Amazon loved that so much, they went, NAFA, we're going to buy you. And now NAFA is doing great things at Amazon, including launching A-class ARM-based instances that are based on a homegrown chip from Annapurna that they can grow on. My startup actually does accelerators and presents them as NVMe. So we're not an SSD, we're an FPGA accelerator, but we don't expose ourselves as an FPGA accelerator. We tell the host we're an NVMe device. I'll talk about that a little more in a minute. And I'm running so far behind schedule. Here's a quote from yesterday. Michael Cornwell, who runs storage at Azure. So Azure is a pretty big storage company right now, one of the biggest on the planet, and certainly one of the largest consumers of NVMe on the planet. And one of the things he said in his keynote at the NVMe Developers Day yesterday is, don't think of NVMe as a storage protocol. It's a transport. We can do a lot of interesting things with NVMe that don't have to necessarily be directly related to an SSD. It's a transport. It's a language for communication. Why NVMe? Why don't we invent some new standard for talking to computation? We could call it CNVE or CompE or something like that. But the problem is, if you did that, you would actually find that what you invented, this new standard that you had to define from scratch, was about 80% overlap with NVMe, probably more than 80%. Because from an accelerator point of view, what you want is low latency, high throughput, i.e. good DMA. You want to have low CPU overhead. You want to have multi-core awareness. You want to have quality of service. And that's what NVMe, this should say NVMe provides. Sorry, there's a typo. There we go. But NVMe gives you all of those things. And actually, when you think about it, the question should really be, why not use NVMe? Right? Why do I have to go write a new driver from scratch? Why do I have to do something else? The other thing is that we're starting to look at deploying these accelerators at scale. I'm not putting one of them in a server cupboard. I'm putting 20,000 of them in my data center. Microsoft have publicly said every compute node they ship has an FPGA in it. Every single one. And Microsoft are shipping at least 20 servers a week. More like 20,000. They need to manage those. They need to know when they break. They need to know where to find them when they break so an operator can replace them. They need a management stack. NVMe has a really good management stack. And it's a management stack that someone like Microsoft is already comfortable with because they're deploying hundreds of thousands of NVMe drives a month. So they already manage many, many NVMe devices. Why couldn't some of them not be SSDs, but instead be accelerators? Or accelerators combined with an SSD, or NICs combined with an accelerator with an SSD. So I got to do a little plug on, my CEO said, you have to put in a slide about us. I'm like, I don't have to put a slide about us. I'm the CTO. He's like, OK. So we basically take FPGAs from Xilinx. So inside this is an FPGA from Xilinx and some memory, I think from Samsung, actually. And we expose it as an NVMe device. So it's a PCIe accelerator, doesn't have any NAND in it, but it talks NVMe. And we can put all kinds of accelerator functions on that FPGA. We have our own offerings, and we also offer this as a platform to others to integrate their accelerators. So today we do a lot of storage stuff, and we work with a lot of storage vendors like Dell and HP and so forth. But we can also start getting into things like artificial intelligence and pattern recognition and database acceleration. And this is something that we're shipping today. This is PCIe Gen 4. This is 4 lanes. It's a U.2. So I get 8 gigabytes per second of ingestion and egestion if my system runs at Gen 4. I could obviously have other form factors that are different. But we like this one because it's very consumable by NVMe storage servers, because we can plug them in where the drives live. This is a product by a small company called Samsung. I do like this one because you can't even see your logo on it. So I don't know if Xilinx like cropped it out. It almost looks like it's been photoshopped. So anyway, and it kind of shows you, this is your SSD controller. This is like doing like teraflops of operation, like LDPC, error correction, blah, blah, blah. And it's like this nice little small thing. And here's the FPGA. It's really, yeah, it's really, really big. But the idea here is, and this is a very interesting one, is to take that NVMe capability and to provide computation as well, and then have those in the same place and do interesting things in software. A smart SSD. There's a company, a startup called NGD Systems, based down in Irvine. It's a bunch of former STech HDST people. And they're doing almost the other extreme of this. So not putting an FPGA beside the SSD, but actually adding additional ARM cores to the ones they need to the silicon that is the SSD controller. And they expose that through an API that allows them to push Docker containers down to those application class A cores on the SSD, and also provide a mechanism by which those Docker containers can access the data that's on the SSD. So now you can sit there in your lovely Linux world, or even on a Windows laptop, and you can write Docker container files. You can Docker build, you can Docker push, and you're actually pushing to an ARM-based application class processor, and you can have things like compress the data that's at these LBAs, and the SSD will do that internally without having to go off the SSD in order to do that. Insane? Crazy? Is it crazy awesome? Is it awesome? Is it crazy awesome? I don't know. The market will decide. But they're another founding member of the standardization process, because they know that in order to get the software written to make this all work, there needs to be an ecosystem. Very quickly, I want to talk a little about this. How do we make data flows more efficient now we have these smart PCIe devices? So I almost need my little thing. I don't know how well this is going to work, but let's try it out. Whoa, let's get crazy. Ooh, look at that. Oh, I don't like the lag. I hate that. Don't like that at all. I'm going to jump. So in any operating system today, when you ask to move data from one PCIe device to another, so these don't have to be NVMe SSDs, any PCIe device to another, that DMA has to go through system memory that's hanging off the processor. Now, with DDIO, you might hit the last level cache, maybe, but you probably end up going out to DRAM. So that means that to get data from here to here, I got to go up to the processor, out to DRAM, and then come back again. And the problem with that is it creates a choke point on the processor. And also, if the processor is running applications, they have to fight with the DMA traffic to get access to memory. What we have upstreamed in Linux as of the 420 kernel, which is literally in RC cycle right now, is a new framework that any PCIe driver can take advantage of. And what you can do is, rather than DMAing through system memory, if the PCIe device allows it, you can DMA directly to that device. We call it P2P DMA. It's not exclusive to NVMe. Anyone who writes a PCIe driver is more than welcome to update their code. Thank you. This creates a brand new paradigm, because now I can isolate, I can separate these smart NICs and FPGAs and SSDs from the processor that's controlling them. I can separate the control plane and the data plane, which starts to get rather interesting, because it means I could be doing literally tens of gigabytes of traffic down here, and my processor is, all it's doing is issuing I/O requests, which are tiny. So I can get away with wimpy processors running Linux and still achieve amazing data processing kind of speeds. And this is upstream. This has been done before out of tree, so you can do things like peer direct, but it always involves hacking your kernel and putting in out of tree patches. As of 420, this will be supported in Linus's kernel and will get adopted into Red Hat and Ubuntu and all those wonderful distributions, making it much more consumable. So the CPU is becoming less important. It's becoming less important because it can't do as much, and we're finding ways to get around it. So Michael Kagan, who I know pretty well, is the CTO of Mellanox. In about 2014, he said to me, the central processing unit, I want it to become known as the computational periphery unit. I want the data plane and the control plane to be separated. And I went, OK, Michael, whatever you want, because we're good friends. So basically, what I'm saying now is, we can go even further than that. We can go computational periphery unit. It doesn't need to do any of the compute. It can be the control plane unit. So we're going from CPU to CPU to CPU. And Michael was so happy he bought me some wine. So I wanted to take a very extreme example of that. I was like, let's find the wimpiest, for want of a better word, shittiest, Linux-capable core we can, and let's see how much data plane processing we can do with that. So I went to my friends at Sci5, because they have a Linux-capable core. This is the slide I put up. But the idea is we're going to try and do a lot of traffic down here with very little up here. So what we did is they have this like $10 card, and it's not even like an A53. It's like the equivalent in terms of like Drystone MIPS is like nothing. This thing is like barely Linux capable, but it is Linux. You can run Debian or Fedora on it. So we set it up to run Linux. It doesn't even have its own PCIe yet. You have to use an FPGA to generate a root port. And then we connected that at PCIe Gen 2, not 3, to a Gen 4 switch. And so what we had was basically this little prototype board connected through an FPGA to PCIe Gen 2, connected to Microsemi's new Gen 4 switch. And from the Gen 4 switch, we hung our U.2 and connected at Gen 4. And then we connected a bunch of drives. We actually had some Samsung drives and some HDST drives. And we ran our API, which sits in user space above the NVMe driver, to do offloaded compression. We basically were reading data from this drive, peer-to-peer DMAing it into the buffer here, compressing it, and then writing the compressed data to a different drive. And we were able to get about 5 gigabytes per second. And to be honest, if we had more drives, I think we could have scaled that up. All right? There was no traffic. Like the traffic going up to the processor was literally kilobytes per second, because all it was doing was issuing I/O. And in fact, I have a picture of the hardware. We live for this, right? This is the RISC-V development board that's running Linux. It's running Debian. This is the FPGA board that's generating my root bridge and giving me PCIe Gen 2. What we should have done, this is why I'm not a marketing guru, I should have got a paper clip, because I didn't need more than a few kilobytes per second, and done like a PCIe Gen 1 by 1 connection to this. This is the eval card for Microsemi's new Gen 4 switch. So we go here from like half a gigabyte per second to lane to 16 gigabytes per, 16 gigabytes per second to lane. And then we hang our card off here, and these cables go off to the SSDs, which are actually over here. Kind of insane, but it actually worked. And what happened is we were doing about 6 gigabytes per second of I/O underneath that Gen 4 switch, while this poor little guy, if we tried to DMA through him, we'd be lucky if we got even 100 megabytes per second. What is the message here? The message is the processor doesn't matter anymore. I can do incredible amounts of meaningful work with a very inexpensive processor. I don't need a Xeon. I don't need Naples. I don't need Rome. I can now decouple my PCIe performance from what my processor vendor is doing. Anyone know of a large CPU company that fucked up PCIe Gen 4 so bad? Intel inside, right? This allows us to avoid that. I'm going to wrap things up. I'm going to move a little more quickly there. I'm going to skip the next slides, but they'll be available for people to see. That was a kind of toy demonstration. At Supercompute, we did a more serious version of what I showed you just previously. We actually took a production-grade HP server from HP with AMD EPYC processors inside. So this is a 2U, 2-socket server. It's an NVMe server. It has 24 U.2 drive bays on the front. We put in 6 no-loads. We put in 18 Samsung NVMe SSDs. We offloaded 150 gigabits per second, so over almost 20 gigabytes per second of compression from the host processor. The host processor, we were 70 times more efficient. We were 4 times more space efficient. We were about 20 times more power efficient for achieving the same amount of throughput. And while this thing was running, while we were doing 20-odd gigabytes per second of compression, the cores on the AMD were at 4% of utilization. Of the 64 cores that were there, we were using about 2 of them, which means there's 62 cores, 100% free to run applications. And also, because we're doing peer-to-peer, the memory subsystem is not being taxed. So the quality of service for memory accesses for those 62 remaining cores was phenomenal. Basically, those 62 cores don't even know that we're doing 20 gigabytes of data processing underneath them. Now, start putting RocksDB on top of that, or some other key value storage engine, and it's interesting. Start doing artificial intelligence or VM hyperconverged environments, it starts getting very interesting. Okay, so these are the building blocks, and we need to keep building on top of them, and that's what we're planning to do. I'm sorry for the sake of time, I got to jump that last example, but it's in the slides if you're interested. So some of the conclusions, computer architectures are constantly changing, and they're changing again in a very interesting way. Even David Patterson said so. Do not expect code on your processor, on your CPU, to get significantly faster anytime soon. Dennard scaling and Moore's law are real, and we're not going to see any major changes to that in the near term. Accelerators are definitely the new cool. Heterogeneous compute, the rise of the smart devices. These are the smart NIC, SSD, FPGA, etc. They are not Intel inside. There is opportunity for ARM here. There's opportunity for new ISAs like RISC-V here. Okay? Where there's disruption, where there's opportunity to deploy new code, there's opportunity for ISA disruption. Adding peer-to-peer DMAs to that mix is awesome, and it's supported in Linux today. We have to standardize this. Right? I'm doing a startup in space. Part of me is like, keep it proprietary. That means no one else can compete. We'll make loads of money. It's not true. It's not going to work. It's just going to fail as a market. We have to standardize. We have to open source. We have to push code into Linux. We have to push code into TensorFlow, into glib. All of these things have to be updated and have to be done in a vendor-neutral way. If idiots can't consume it, it won't work. Right? If it's not as simple as just plugging it into your system, people won't get it. And the question I have is, will NVMe potentially be the driver that rules all of this? Is this the one that can rule them all? So thank you very much. These are my babies. This is my lab. And these are my other babies. So I want to thank you.